Hello everyone, I'm Wei Tan. Today I'm going to introduce the concept of macromechanics of a ply. This is an essential concept in the mechanics of composite material. Firstly, let's define what is a ply or lamina. In a fiber reinforced composite laminate, a lamina is a layer, either flat or curved, of unidirectional fibers or woven fabric in a matrix. A lamina is the basic building block of laminates. So what is laminate here? A laminate is assembly of many layers. For example, here you can see we have shown 4 layers, 0, 90, plus minus 45 degrees. Note that in general the orientation of each ply will not be the same. There can be any degree within the plane. The question here is, how can the behavior of a laminate be determined? You could do that by experiments or by analysis or based on the behavior of a single lamina, particularly the stiffness and the strength of a single lamina. So let's go to calculate the stiffness of a lamina. Stiffness of a lamina. Let's start with a simple example of orthotropic materials. Suppose you have a short fiber composite where the orientations of the short fibers are randomized. Therefore, you can approximate the lamina as an orthotropic material. One key concept we need to know is the Poisson ratio effect. As you can see here, if the fiber is aligned in one direction when you apply your loading, then you could actually cause some contraction from this is the original shape. And the elongated part is the deformed shape. As you can see, the material actually contract in the transverse direction. Based on the definition of Poisson ratio, basically you can work it out. The Poisson ratio essentially is the lateral strain, okay? Lateral strain divided by the longitudinal strain. In this case, you can actually think about lateral strain is epsilon 2 and the longitudinal strain is epsilon 1. So basically we want to ask the questions, if we load it in the one direction, the longitudinal directions, what is the Poisson effect, the strain caused in the transverse directions? We can rearrange these equations and we can get epsilon 2 equal to minus nu, okay, times epsilon 1. And from our basic definition of epsilon 1 is essentially the longitudinal stress divided by the Young's modulus. Therefore, when we come back here, we can essentially get this equation here. Alright, so I have shown a quick derivations of that Poisson ratio strain, transverse strain caused by the longitudinal stress. And similarly, if you load it transversely, this is the original lamina. and then you load it transversely, you will cause a contraction again in the longitudinal directions. You load it in the 2 direction, but it will contract in the direction 1. Therefore, we get these derivations again, very similar. With that in mind, now we can actually look at if we are applying multi-axial stress, not only uniaxially. Now we are applying stress in 2 directions, sigma x and sigma y. What will happen? In such case, you need to consider the Poisson ratio effect. For example, in the x directions, it will not only generate the strain caused by the sigma x, but also there was some strain caused by the Poisson ratio effect from the sigma y, which is here. So that's why you need to use the Poisson ratio and times the transverse strain, which will cause some contraction in the longitudinal directions. Okay, so that is the 4 expressions of epsilon x. Similarly for epsilon y, you have a strain in 1 direction here, but x stress will cause some contractions. Basically, that's why contraction meaning is in a negative strain, which is the second half of these expressions. And we don't have Poisson ratio effect in the shear direction. Therefore, we simply use the shear stress divided by shear modulus, which is given by these equations here. Now, we can simply express the equations in a matrix form. Just if you go back to the equation like this one, you can think about taking out the epsilon x, taking out epsilon y, and gamma xy. Okay, that is the left hand side. And you can take out the common terms. Let's think about sigma x, sigma y, and tau xy. You put them in the other part. And then you just need to find out the missing term in this matrix. Okay, the 3 by 3 matrix. Essentially, you will find out. Let's just use one example to illustrate that. Now you have, okay, 1 over e here, and for the second term, this is minus nu e, and we don't have the contribution here for the tau xy. Therefore, in this case, this is just 0. You can expand this equation. You will see epsilon x will equal to the first term times the sigma x, and then the second terms times the sigma y, and the third term times tau xy, which essentially is the same equation here. Now we're just writing all of them in the matrix form, and this is the final answer here. Effectively, this is the compliance matrix. Compliance is the inverse of the stiffness, right? The higher the compliance means the soft the material. And this can be rearranged to give you actually stiffness matrix. Essentially, this part, if we give that as a S, if you do the inverse of S, you will get the stiffness matrix, which is the bottom part. Okay, and this basically is the inverse of a matrix, which you have learned in your first year matrix algebra. Alright, now let's look at the stiffness of a lamina, particularly for orthotropic materials. Now, if you look at the composite lamina, you need to distinguish the modulus in each direction 1, 2, 3. Okay, that's why typically we put there modulus E1, E2, E3. And there's also shear modulus G12, G13, and G23. The concept here is very similar. And let's consider if it is a plane stress conditions where you just have a very thin lamina. Okay, and is subject to the in-plane stress sigma 1 and sigma 2. Note that the coordinate axes are at the moment are aligned with the principal material axis. Again, based on the Poisson ratio effect, you will have the strain acting as the one direction epsilon 1 will equal to the strain caused by the sigma 1 and the Poisson ratio contraction strain caused by the sigma 2. Okay, these two terms. Similarly, for the epsilon 2, you will get two terms. And shear strain is not dependent on the Poisson ratio effect. And similarly, like here. Now you can write similar things. This is the Poisson ratio I have mentioned already. And we can basically write the equations in the matrix form. Okay? And this is a compliance matrix. Now we can distinguish each term with a certain expressions. S11 equal to that first term, S12 equal to the second term, and it can be shown that the matrix is symmetric such that this part is equal to this part. So that's why you can have these two terms essentially the same. Okay, the Poisson ratio here actually has a major Poisson ratio and a minor Poisson ratios that link these two up. As we have done something similar before, we can rearrange the equation such that before you have written as strain is equal to a compliance matrix times the stress. Now you can inverse that matrix such that sigma is equal to S minus times the strain. This is a more typical equation we are looking at. Stress is equal to the stiffness times the strain. Okay, the stiffness matrix is equal to the term shown here. We use Q here, Q11, Q12, etc. And in a condensed form, this equation become like epsilon 12 equal to S times sigma 12. Sigma 12 is equal to Q times epsilon 12. Okay, 4 elastic constants are required to characterize these stress-strain behaviors, like E11, E22, nu12, and G12. Right. As you can see, this is a table for some classic examples: CFRP carbon fiber, reinforced polymer, and glass fiber and Kevlar. They have their, you can see with a certain fiber volume fraction, they have their 4 constants listed here. Now let's look at if the stiffness changes. If you have a layer where the fiber is not aligned with your original principal directions, or you have defined 1, 2, that is essentially 1, 2. Originally we assume that is the material axis. The fiber means 1, the transverse of fiber means 2. And we can also define a so-called global axis, where the global axis is x and y, but your fiber can be aligned somewhere in a certain orientation. In that local coordinate system, you can have your 1 and 2, right? So stress-strain relation here now can be write as epsilon 1, 2 equal to S sigma 1, 2, and you can similarly use the Hooke's law expression sigma 1, 2 equal to Q stiffness matrix times epsilon 1, 2. So now we want to ask the questions. If you rotate your fiber orientation to a certain degree, how do you actually calculate the stress in the global coordinate system? Right? You can easily calculate that in the material axis 1, 2, 1, 2. But how about the stress in the x and y coordinate system, which typically that is the direction we are looking for? Okay, we need to determine the relationship between sigma xy and sigma 1, 2, and between epsilon xy and epsilon 1, 2. Basically, we can do something like stress transformation. Suppose you have the original material stress at 1, 2. Now you want to rotate your stress to the x and y. Suppose that angle is theta between your x and 1 axis. And we can use this stress transformation matrix to find it out. And denoting the transformation matrix by T, we can write sigma 1, 2 equal to T times sigma xy. So basically, it's material axis stress material, okay? And this is a global coordinate system. And we can simply actually establish a similar transformation relationship for the strain, where epsilon 1, 2 is equal to the transformation matrix times epsilon xy. If you go back, you'll see this is the stress and this is strain. And where the modified strain vectors we call tensorial strains can be written as this form, epsilon 1 and epsilon 2, and gamma 1, 2 over 2, epsilon x, epsilon y, and gamma xy over 2. The tensorial strain essentially has some difference, where the particular difference is the shear strain. You can use epsilon 1, 2, which is half of its engineering shear strain. So this is called engineering strain. And this is called tensorial strain. Okay. Now, this can be related by this we call natural strain vectors. Essentially, just to mapping out the two times difference of the tensorial strain and engineering strain. Okay, R is here. It's not a transformation matrix, just a scalar factor matrix. Now let's look at the transformation equations for both strain and the stress, listed here. Right, so let's rewrite that equation where sigma xy is essentially the inverse of that transformation matrix and times the sigma 1, 2, similarly for the epsilon xy. And essentially t minus 1 is the inverse of that transformation matrix. Okay, it can simply become, instead of t theta, t minus 1 theta is equal to t minus theta. Okay, that's how it works in this case. And the stress strain equations in 1, 2 axis can be written as sigma 1, 2 equal to q times epsilon 1, 2. This can be written for the xy axis by substituting sigma xy equal to t minus 1 sigma 1, 2. And epsilon 1, 2, as we said before, now epsilon 1, 2 is equal to r times the epsilon 1, 2 bar. Okay, and r, then because we know we have this epsilon 1, 2 equal to t times epsilon xy bar, we can further expand that equations, and we can also further rewrite that because epsilon xy is basically r minus 1 times x epsilon xy. Okay, this is the engineering strain, this is the tensorial strain. Oh, I think the other way around. This is the tensorial strain, this is the engineering strain. Okay, and now we can do something where we replace the whole term here by essentially equal to q equal to the right term here, which essentially is equal to the epsilon 1, 2, right? Let me just explain that a bit clear to you. So this is equal to 1, 2, like the blue equation shows, and then we replace the epsilon 1, 2 by this whole term. It becomes q times r t r minus 1 epsilon xy, which essentially is the equation here. And we can simplify the whole term by just put an equivalent stiffness matrix q bar. Okay, so the whole equation can be simplified by this one, and this we can also call this q bar as reduced stiffness matrix. Okay, you can also call it equivalent stiffness matrix, such that it can link the sigma xy to epsilon xy in the global coordinate system. Right, so this equation can be inverted to give epsilon xy equal to s bar times sigma xy. So where s bar is q bar inverse. Alright, and we can actually derive the q bar based on this equation here, and we can expand the expressions for each term. Okay, essentially it's dependent on the q and also the m and n. If you remember, mn is the term in the stress transformation equations, where m equal to cosine theta, n equal to sine theta, right? And similarly for the reduced compliance matrix, it can be written in terms of S. So if we substitute these things to the matrix, you will get something like this, which is the compliance matrix first of all. And we can also derive the apparent engineering constant from the equation we got. So we know after we rotate the material directions such that we can find the global equivalent modulus x and y, ex and ey and gxy, etc. Note that in general QNS will be fully populated. Okay. What is the significance of these equations? Consider you have an off-axis reinforced lamina subjected to a stress in the x direction only. For this case, the resulting strain are given by this one, where you only have the unidirectional stress. Then we can simplify the equation to this one. Essentially, if the S13 is not 0, then gamma xy is not 0 either. And essentially, it elongates the materials. This is something we can observe in the experiment as well, right? When you load it for off-axis samples, you will see a very long uniform deformation of the materials. Right. I think that's all we have. We may have some other things you want to answer. Okay. For example, how are these four elastic constants determined? You can determine by experiment. You can determine them by analysis from the fiber and matrix properties, which essentially is the knowledge from our part 2, Macromechanics. You use the Roth mixture to calculate the equivalent modulus or strength based on the volume fraction of your fiber and matrix. Okay, if this is the fiber and the rest of them are matrix. Okay, right. I think that's all for today.